It's my great pleasure to introduce Batuhan to give a talk on group testing in structured and dynamic networks. So this has applications to COVID-19 and other emergent epidemics. So we don't often have people from the electrical computer engineering field give a talk. So really interested to hear about your work, Batuhan. And just a reminder to everyone that the session is being recorded. And Batuhan, the floor is yours.
Okay, thank you for the introduction. And before starting, I would also like to thank Bethany and our advisors, David and Sophia, for their kind invitation for this talk. So today I'm going to talk about group testing in structured and dynamic networks, which is our research work with my thesis advisor, Professor Shanur Lukush. So what is group testing? Group testing is basically an efficient infection identification method based on pooled testing. It was originally proposed by Dorfman during Second World War, and it's basically based on the pooling of the test samples of people instead of individually testing their test samples for infection identification. So especially with the emergence of COVID pandemic, we all know that efficient testing and efficient infection identification is basically like the most important method for early pandemic controls, or like it is one of the best methods for infection, for dealing with infections. So here we can just go over this example in this bottom figure to have an idea about what is really like the main idea of group testing and what's it based on. So for instance, here we have 16 people and there's one infection among them. So normally, like the trivial method of infection detection in this population is that you take 16 samples, test samples. It can be like blood samples or like swab samples, like in COVID case. And then you perform 16 individual tests to identify their infection status. However, like group testing method says that, okay, we can basically pool these test samples and mix those samples and test those mixed samples instead of individually performing tests. So for instance, here in this example, we have groups of 4, like the first row of 4 people are grouped and second row and so on. And then those mixed samples are tested. So here, by mixing those samples, we have something like logical binary or channel of these test samples. So basically, if a mixed sample is negative, we know that all of the samples mixed and in that mixed sample is negative. However, if we have a positive mixed sample, it doesn't say so much. It just says that, okay, so that group has at least one positive sample in it. So here, for instance, in this example, first, third, and fourth groups are negative. So by just performing these 3 group tests, we identify all 12 people. However, like for the second group, the mixed sample is positive, so it says that there's at least one positive. And in the second round, what we do is we perform another round of individual tests specifically just for this group. And at the end of the day, everyone's infection status is identified with just 8 tests. In the first round, 4 group tests. In the second round, 4 individual tests. Like in compared to performing 16 individual tests, it's of course like halving the number of tests for full identification. So basically, it says that, so the whole point of group testing is infection status of n individuals can be identified with less than n tests. So as I said, main objective is identify the infection status of people, and the utilization that comes from is the utilization comes from the idea of pooling the samples, like mixing samples and testing those mixed samples. And like as a result, we can identify these people with less than n tests. So groups do not have to be like disjoint as in the example that I showed you. For instance, like this example is also a group testing scheme. So first we just mix samples from like all 4 people, and then we might have some groups of like first 2 and the second 2, and also we might have some individual testing in it also. So Dorfman's original algorithm was basically the algorithm that I just described in the first figure. Like first, like find the group size and then specify, like uniformly randomly specify those groups. And then in the first round, perform these group tests. In the second round, for the positive groups, perform another round of individual tests. However, like after Dorfman, for decades, there have been like many variations that have been studied by scientists from different backgrounds and different areas. So here I will talk about some three classical major distinctions of group testing studies. So the first distinction is like the infection models, about the infection models. So classically, in classical group testing works, there are two major infection models. The first one is combinatorial group testing, and the second one is probabilistic group testing. So in the combinatorial group testing, the assumption is the following. So we assume that there are D infections in the system out of these N individuals in total, and it makes a possible infected set number N choose D. So out of these N choose D possible sets, one of them is the true infected set. And the question is, like, what can we do for identifying this true infected set with the minimum number of performed tests? However, in the probabilistic group testing, it is, as the name implies, we have each individual infected independently and identically with probability P. So it makes in total N times P expected infections. So also in the group testing literature, there is this another major distinction, which comes from the recovery models. So we have either exact recovery models or probabilistic recovery models. In exact recovery models, we have this constraint of independent of the infected set realization, we need to find this infected set with probability 1. However, in probabilistic recovery, it's like we might have, we have some room for vanishing error probability for recovery of the infected set. And finally, the last major distinction that I want to talk about is about the test designs. So there are two major test designs in group testing studies. First one is adaptive, and the second one is non-adaptive designs. In adaptive designs, tests are done in multiple stages. So you perform some set of group tests and you get the results. And in the second round, you perform another round of group tests and so on and so on. Like it can go all the way to, I don't know, like K stages. And so here the advantage is you can utilize the past results. However, in practice, most of the times this is not what you would want, because like you don't want to wait for test results for each of these stages. In practice, it might result in really long time of infection identification. So in non-adaptive designs, all tests are constrained to done in a single stage. So you have to specify the group tests, you have to specify which samples to include, which tests at the beginning. And after you perform all these tests, you cannot perform another round of tests. So again, going back to the Dorfman's original algorithm, as I described in the beginning, it is like an adaptive algorithm, but fixed to 2 stages. So yeah, for the practical concerns, non-adaptive algorithms, of course, is preferred because you can, like, all these tests can be done in parallel. However, like these distinctions are not the only distinctions in the group testing literature. It's a vast literature, and there are many variations that have been studied, such as noisy test results, where the test results are not like perfect. They can flip with some, depending on some random statistics behind those, or like counting the infections. In order to count the infections in a population, we can also utilize group testing methods. Or like for more practical concerns, fast decodings or like explicit algorithm designs are also considered. However, today's talk is about these 3 sub-branches that I highlighted with blue, which is like our research falls under these categories of these 3 categories. So in non-IID infections, people basically challenge the IID infection models. So in IID infection models, as I described in the probabilistic group testing studies, it is assumed that everyone is infected with the same probability P independently. However, in practice, we know that there is some correlations between people. So the infection status of the population is not really independent at all, or like not identical as well. So in the second one, this is like these bottom two ones are more recent works. So the network structure-based infections is basically also a non-IID infection case. So here the infection spread or like the infection status of people also depend on their interactions and their like communication between each other. So basically there's this also side information of network of people that can be utilized further. And finally, we have dynamic group testing structure. So far in all these classical works, the problem is static in the nature. So you have some N individuals and you have some infections among them. And you are asked to find those infections in the system. However, again, in practice, such as in the COVID-19 case, we know that testing and like identification and isolation, all these things, also infection spread itself, it's a time span. It's not like a static problem at all. Like you day by day perform tests, day by day infection keeps spreading, etc. So in order to challenge the static nature, we also have some dynamic group testing works. In our work, in our research, basically we challenged two different dimensions of the group testing problem. And we propose two major frameworks. First one is group testing with a graph infection spread model. And the second one is dynamic infection spread model based group testing. So I'll talk about both of them in detail. So the first framework is group testing with a graph infection spread model. So in this work, in this framework, we basically challenge the independent and the identical nature of the classical probabilistic group testing problem. Because we know that infection states of individuals are correlated in practice. And especially if you consider something like a contagious infection, contagious disease like COVID-19, it is more obvious that the infection spreads by interactions between people. Therefore, you cannot really safely assume that the infections are independent or something. And moreover, the most important motivation that led us to this work is that this data of connections between individuals, data of these interactions, basically might be available in practice because we all have our mobile location data, and like we can basically estimate at least the statistics of these interactions between people. So in our system model, we have a random connection graph C. This represents the individuals and the connections between individuals. So individuals are represented by vertices, and like edges represent the connections between these individuals. And it's a random graph, so we don't know the true connections of people. However, we know some probability distribution of the edge set of this random graph C. Furthermore, we have a patient zero in the system, which introduces the infection to the system. And after the realization of these connections of individuals, we say that everyone that is connected to the patient zero is infected, they get infected. So if you think about it, like intuitively speaking, the exact edge set do not really determine, like more important than the exact edge set, the important thing that determines the infection status of people is the cluster formation in this random graph. So after the edge set realization, we have some realized clusters in the system. And basically these clusters determine the infection status together with the patient 0Z, which is also uniformly randomly chosen from the individuals. And in our work, we consider cluster formation trees, where possible cluster formations can be like in a tree-like structure. So intuitively speaking, this can be taught so in a department, let's say, in a university building. So those clusters, possible clusters, can be individual level clusters where maybe there is no interaction at all, people wear masks, etc. So in that case, clusters might be individual leveled, or like maybe in another level of cluster formation, it might be the case that clusters might be the size of labs of students, or like department level clusters we might have. So we basically consider those cluster formation tree-like structures in our consideration of cluster formations, possible cluster formations in the system. And then we propose two-step sampled group testing algorithms, which consist of testing and decoding phase. In the testing phase, we have we select a sampling cluster formation out of possible cluster formations that random graph can have. And we have a sampling function that selects exactly one individual from each cluster in the selected sampling cluster formation. And finally, we design a zero-error non-adaptive group testing matrix to perfectly identify these selected individuals. As I said, like in the first step of the decoding phase, those selected individuals are identified with zero error. And in the second step, after identifying those selected individuals with zero error, we assign their infection status to everyone in their cluster, everyone in the same cluster. So this introduces some false classifications to the system because we do not know the true cluster formation in the system. But instead, while designing the algorithm, we select one of these possible cluster formations to do this. And this results in some false classifications, as I said. And also, because of that, this choice of FM, the sampling cluster formation, results in a trade-off between number of required tests and false classifications, which I will also show with the numerical results at the end of this section. So this is just a toy example. Of course, the real systems in the practice would be like much more individuals, much more possible cluster formations, etc. But for the sake of just giving a toy example, we have this system where there are 3 possible cluster formations. So we have 10 individuals. These are different clusters. So first 3 individuals, for instance, in F1 cluster formation, we have first 3 individuals in a cluster, 4 and 50 individuals in another cluster, and the rest of the people in another cluster. However, when we go one level below in the possible cluster formations in F2, we see that, for instance, this first cluster is split into 2 different clusters, and so on and so forth. In the third cluster, this cluster just split into 2 different clusters. So we know in our system, we assume that we just know the probability distribution of realization of these cluster formations. We do not know the exact cluster formation in the system because it's a random graph, and but we know the probabilities. And then what happens is that while designing some group testing algorithm, we first select the sampling cluster formation out of these 3 possible cluster formations. So imagine that we selected FM to be F3. And then we have to pick exactly one individual from each of these clusters in F3, but exactly one individual. And then, so imagine that we've selected 1, 3, 4, 6, and 8 individuals. And then we have possible infected sets like this, because due to this given possible cluster formations, these are the only options of possible infected sets. And we propose and design a F-separable test matrix we call for perfectly identifying these selected people with zero error. So yeah, I can skip the details of this F-separable test matrix construction, but at the end of the day, what's important is that it guarantees the identification of infection status of these selected individuals. And after that, after identifying these first, third, fourth, sixth, and 8th individuals, what we do is we assign their infection status to the other people in their own clusters in the sampling cluster formation selected. So as I said, this might result in some false classifications because we do not know the true cluster formation. So in our work, we characterize the expected number of false classifications, both conditioned on the true cluster formation or without conditioning. Furthermore, we also characterize and give some lower bounds on required number of tests needed in terms of the parameters of the given possible cluster formations. And moreover, we also have some complexity results. What is the complexity of finding the optimal sampling function, or what is the complexity of constructing the F-separable test matrix, or the decoding complexity, so on. But moreover, we have also, by using these general results that we derive, we also have this subclass of cluster formation trees, which is exponentially split cluster formation trees, which has some more specific properties. So at each level, for instance, it has to divide into 2 same-sized clusters, etc. And then for these exponentially split cluster formation trees, we specifically characterize the expected number of false classifications and also required number of tests. And here we also have these comparison results. So here in this framework, basically like the big picture of this framework is that, so we have this side information of connection between people. We have this side information of this random graph of people's connections. And by just utilizing that, we can have some like real improvements, some big improvements over known classical group testing algorithms that do not utilize these things at all. So for instance, even though we assume that adaptive group testing, we can use adaptive group testing in classical works. And also, even if we assume that we exactly know the number of infections in the system while designing these tests, the resulting capacity is order of n over log n. However, we show that for exponentially split cluster formation trees, we can achieve an upper bound of tests order of log n, basically. So with log n tests, with order of log n tests, we can identify these infections in the system, even though there are like many expected infections, like order of n over log n expected infections in the system. So this is like the big picture of this framework is that we can utilize these things and it can result in really huge improvements. So after that, we have some numerical results. We also implemented these algorithms in our simulations. And then, for instance, here, we can see the trade-off between this selection of sampling cluster formation between the expected false classifications and the required number of tests. Like, as I said, there is this type of trade-off. So with the change of sampling cluster formation selected for algorithm design, we see that number of required tests increases as we go in lower levels of the possible class formations, while expected number of false classification decrease. Also, in order to show that our ideas and our approach to the problem can be generalized into arbitrary systems as well, we also implemented and simulated an arbitrary system, which is not a cluster formation tree, which doesn't result in some specific like exponentially split cluster formation tree-like structure or something, but we just have a random graph where edges realized independently with some probabilities, and there are more than 500 possible cluster formations, and this does not yield a cluster formation tree. However, by using our ideas, like considering some specific sampling cluster formation, picking exactly one individual from each of these clusters and identifying them and assigning their infection status to everyone in their corresponding cluster. So by using this idea, even though it's not a cluster formation tree, and even though we do not have a generalized theoretical results for these arbitrary systems, we see that in our numerical results, we can use these ideas, and it results in improvements. And moreover, like we can use some probabilistic assignment, randomized usage of these sampling cluster formation selections, and we can achieve these dashed lines, which are the convex combination of these points as well. So this is the expected number of false classification versus choice of sampling cluster formation curve. And this is the corresponding required number of tests versus choice of sampling cluster formation curve. Again, we see a similar trade-off between expected false classifications and required number of tests. However, it is still in the order of log n, required number of tests, as we see at maximum it's 7. So this ends our first framework. And then after this framework, we also considered challenging the static nature of group testing. So as I said, like majority of the group testing works before, and all of these classical works considered the single shot problem, which is okay, we have n individuals, we have some infections among them, and how can we detect those infections? That was the static problem that all the classical work considered. However, as I said, we know that in practice, such as in the COVID-19 case, it is a dynamic problem. Infection status of the people is dynamic. So it changes over time. people get infected, people get recovered, people get isolated and stuff. All these stuff just dynamically evolves. And also testing itself. Testing is also not static. We perform those tests over time. So basically these things, these practical considerations motivated us to propose a framework that reflects these practical dimensions. So basically, like, yeah, as I said, as I described, in practice, we need to consider a dynamic system. And moreover, the one point that I missed to talk about is that the number of available tests at each time instance is also limited in practice. So all these classical group testing works considers this main mathematical problem of what is the minimum number of tests for full identification. However, in practice, we know that we have some limited number of tests, and we need to utilize that minimum number of tests, that available testing capacity, to do our best. It's not like we have unlimited number of tests and what is the minimum number of tests that we can use for full identification. The problem is never that in practice. So we also considered this in our dynamic system. So our dynamic system is based on the SIR model. So SIR model is like used for disease spread modeling and like this infection modeling. I believe the audience might be like more knowledgeable than me at this SIR model. So we consider something like with probability P, each individual is infected independently at the beginning. So this is like the T is equal to 0 case. And moreover, like time in our system is discrete. It's like, we can think of it like, day by day testing or like day by day infection spreads. So we consider discrete time. And at each discrete time instance, we have two consecutive phases. So infection spread phase and testing phase. In the infection spread phase, we consider that each non-isolated and infected individual infects each susceptible individual with probability Q independently. So as I said, these N individuals are divided into 3 disjoint groups in the system. So each individual at each time instance is either susceptible, which means that never got infected and open to get infected. They can also be non-isolated infection, which means that they are infected, but they do not know that they're infected, and they infect other susceptible individuals. They can infect other susceptible individuals. And finally, we have recovered individuals, which are infected at one point, but they are isolated and just eventually got recovered. And they cannot infect others. They cannot infect other susceptible individuals. So basically, because of like this thing, we have that at each time instance, at each discrete time instance, at infection spread phase, we say that each non-isolated and infected individual infects each susceptible individual with probability Q independently. So this is like, if we have S susceptible individuals and I non-isolated individuals, we have S times I different independent Bernoulli random variable, which realizes with probability Q independently, which models the infection spread from non-isolated infections to the susceptible individuals. And finally, in the consecutive phase, at each time instance, we have this testing phase. With the available t-tests that we can use, those t-tests are performed. And after performing these t-tests, some of the infections are detected. Not all of them, but some of them are detected. And we say that after detection, they are isolated and they move to the recovered individual state. As I said, we assume that isolated infections do not change their state and cannot infect others for the rest of the process. I know that in some variations of SIR model, some recovered individuals later on in the system become susceptible again after recovering, or after some time they become susceptible or something. But in our system, we assume that for the rest of the identification process, they stay in the recovered state. As a summary, the state of individuals can change from S to I or I to R. There is no other transition. So S to I transition becomes when a susceptible individual gets infected by non-isolated infection and becomes non-isolated infection themselves, or I to R when testing phase occurs and then we detect some of these non-isolated infections. So in order to measure the performance metric of our proposed dynamic algorithms, for the notation, we have alpha t as susceptible individuals at time t, lambda t as non-isolated and infected individuals at time t, and finally gamma t as recovered individuals, number of recovered individuals. And as you might really just immediately guess, the system reaches steady state when lambda t is equal to 0. Because both of these transitions from S to I and I to R, both of them occurs when there is some non-isolated infections in the system. They either infect other susceptible individuals, or they can get detected and then isolated and move to the state of recovered, like the state of R. However, if we don't have any non-isolated infections remaining in the system, then it is the point where there is no more transition, the system reaches the steady state, there's just some isolated infections, recovered individuals, or like there are some susceptible individuals that never got infected. And as a performance metric, we consider the number of susceptible individuals in the system when the system reaches the steady state. So for this performance metric, we have some theoretical results, but our theoretical results are like general results. So if we consider symmetric and converging dynamic testing algorithms, which satisfy these two criteria. The first one is symmetric criterion, which says that the asymmetric and converging dynamic testing algorithm must be symmetric over individual indices at each time instance t. So whatever algorithm that we propose, it needs to be symmetric over individuals. So for instance, like the probability of some individual being non-isolated and infected at some time instance t must be equal to probability of another individual being non-isolated and infected at the same time t for all times and for all individual pairs. And also we need to satisfy the convergence criterion. So a symmetric and converging dynamic testing algorithm must satisfy this convergence criterion, which is the vanishing probability of being non-isolated and infected at time t. At time t goes to infinity, yeah, not all times. So we propose two dynamic algorithms specifically, and we analyze their performance both numerically and theoretically by using our general results as well. So the dynamic individual testing algorithm is like a baseline algorithm. So what it does is the following. So we have T individuals, T testing capacity at each time instance. And we utilize this T testing capacity by uniformly randomly selecting some non-isolated people. So out of these alpha T plus lambda T non-isolated individuals. So because we know the isolated individuals, and we just exclude those from testing process because we know that they cannot infect others. So we just, out of these non-isolated alpha T plus lambda T individuals, uniformly randomly select T of them and perform individual tests to them. So basically it reflects pretty much what is being done also in real life scenarios, for instance, in COVID-19 testing, let's say, or like other randomized testing structures. This is basically the most trivial and like a baseline method. Just randomly selecting T people out of non-isolated individuals and individual tests. However, in the dynamic Dorfman type group testing algorithm, we propose some group testing structure. So it says Dorfman type because it is like the original Dorfman type algorithm, the original group testing algorithm that's proposed by Dorfman, and I also briefly talked about in the beginning. So what we do in this algorithm is that out of these alpha T plus lambda T non-isolated individuals, we first partition them into T over 2 disjoint sets. So half of our testing capacity is just preserved for this group testing stage. And after these group tests are performed, some of them are just negative. We know that these groups are completely negative. However, like after these T over 2 group tests, we know that some of these groups are positive. And out of these positive groups, we perform T over 2 targeted individual tests, which means that we perform these tests to the groups that we know there is at least one positive. So basically, it's more targeted. However, in comparison to the dynamic individual testing case, these testing capacity is like halved. However, it's like targeted. So it results in a trade-off that I will also show in the numerical results. And moreover, like we consider weak versions of these algorithms to provide some loose lower bound results and loose lower bound guarantees for these algorithms, where we include also the isolated individuals. Yeah, these are our theoretical results. We have some approximate result for expected number of alpha t, the number of susceptible individuals at each time instance. And also for the weak dynamic individual testing algorithm, we also have this steady state result for the expected number of susceptible individuals as the system reaches steady state. Yeah, also, and we have this this result here when there are alpha tilde t and lambda tilde t non-isolated susceptible and non-isolated infected individuals in a system just before the testing phase at each time instance. If this condition is satisfied, then dynamic Dorfman type group testing algorithm outperforms the dynamic individual testing algorithm. For our numerical result, what we do is we simulate this dynamic system of infection spread, testing, and isolation cycles over time, over discrete time. And then after calculating each of these paths, sample paths of alpha t, lambda t, and gamma t, we just do it over and over again, like 1,000 times, to obtain these expected paths by numerically calculating these averages of these sample paths of alpha t, lambda t, and gamma t. And moreover, we also plot our theoretical results to compare these expected paths that we numerically calculate. And we run these simulations for 3 different sets of system parameters. So this is the first set of system parameters. Here we see that in our simulations, we plot, as I said, these red curves are like the numerical calculation of the alpha t, the number of susceptible individuals. Blue curves are the gamma t, numerical calculation of number of recovered individuals. And finally, the black curves are lambda t, non-isolated infection curves. And also in the green curves, we have our theoretical results. So on the top left, we have dynamic Dorfman type group testing algorithm performance. On the top right, we have dynamic individual testing algorithm performance. And on the bottom, we have the weaker version of these algorithms, where we just have some loose lower bounds that perform strictly worse than these original algorithms, but gives us a nice, some lower bound guarantees. So here we see that since our performance metric is the expected number of susceptible individuals at steady state, we see that individual testing algorithm performs better for this set of system parameters than the Dorfman type group testing algorithm. And this is the second set of system parameters, where we see that dynamic Dorfman type group testing algorithm performs much better than the dynamic individual testing algorithm. And intuitively speaking, the conclusion of these, the comparison between these two systems is that in the first system, we have P is equal to 0.2. This means that initial number of infections is high in comparison to the second system. This is just 0.01, meaning that initial infections in the system is actually lower than the first system. However, Q, which is the probability of infection spread, is much lower in the first system than the second system. So basically, it says that in the first system, what happens, intuitively speaking, is that there are many initial infections in the system. And since dynamic individual testing algorithm is just blindly tests T randomly selected individuals in the system, it can basically detect those high number of initial infections in a better way than the dynamic Dorfman type group testing algorithm, because Dorfman type group testing algorithm tries to, in the first half of the group test, it tries to detect some positive groups among these people. And in the second half, it uses targeted testing. So basically, but the initial number of infections is already high and the infection spread probability is already low. So the problem is how fast can we detect those initial infections? However, in the second system, we see that the number of infections is low. So basically targeted testing becomes much more important because we need to find these positive groups and then specifically focus on these positive groups. rather than just blindly trying to test everyone. So even though this dynamic individual testing algorithm uses these t-tests, all of them for these individual testing, and dynamic Dorfman type uses just the second t/2 test for targeted testing, we can see that for the lower number of initial infections, but higher number of infections spread probability, we see that it performs much better than the dynamic individual testing algorithm. And finally, we also have some results of a system where testing capacity is low, initial infections, and also both the infection spread probability is high. Here we see that both of these algorithms basically fail. So yeah, all of them, like almost all of the people gets infected, and like this number of isolations are like almost everyone at the end of the day. So this is a system where both of these algorithms can also fail and cannot control the system. So as a conclusion, depending on the system parameters and depending on the system specifications and what's needed for like what is needed for policymakers or something, we can specifically tailor and select which algorithm that we can use. Either like, is it a good idea to include this group testing approach, or like, is it a good idea to just use individual testing approach? It's all a matter of system parameters and the system specifications. Yeah, so in this talk, that everything that I talked about, and like these frameworks, major frameworks that we considered, are based on our 2 journal papers and 3 conference papers that are listed here. Yeah, I think that's it. Thank you for listening. Yeah, thank you.
Great. Thanks a lot, Batuhan, for a really clear and interesting talk. So I'd like to open the floor up for questions. So feel free to raise your hands, or you can ask your question in the chat as well, and I'll ask it. So while we're waiting for people to do that, could I start with a question about your first piece of work about the graph inspection spread model? So the kind of common belief is that group testing is kind of only useful when there's a low prevalence, because if there's a high prevalence, I guess you would just do individual testing. But I found a really interesting point in your paper was that didn't seem the case in this setting. Would you mind saying a bit more about that?
Yes, of course. That's a great question. So as you said, the common belief about the group testing works is that whenever the prevalence rate is low, we can use group testing to obtain some really nice improvements over individual testing, such as the initial example that I showed here. There's just one infection, and like we performed group tests, and with just 8 tests, we identified everyone here. However, imagine that instead of 1 infection, imagine that there would be like 5 infections in this system out of these 16 people. What will happen is that when we perform this group test, maybe like all of them might be also positive, which means that it is strictly worse than individual testing. It just doesn't say so much. Like this positive test just says that there's at least 1 positive. And because of this, in all these classical group testing works, the results say that, almost all of the results say that, okay, so if the prevalence rate is high, group testing cannot be used. It is like using individual testing makes more sense. However, in our work, we showed that this might not need to be the case for every setting. So if we utilize this side information, of connections of individuals, we can actually use group testing even when the prevalence rate is high. Because like here, what we utilize is that we basically eliminate many possible infected sets in the system. So this is the key point of our framework. We can eliminate these, like going back to the toy example here. So we selected the individuals 1, 3, 4, 6, and 8. These are 5 individuals. And if you think about it, if there's no side information about it, and if it was just a probabilistic group testing case, the possible infected sets might be 2 over 5, 32 possible sets out of these 5 individuals. So out of these 32 possible infected sets, we needed to design some group testing structure to specifically find the true infected set. However, like when we utilize this random graph structure, when we utilize this given side information about the connections of people, we know that out of these 5 people, possible infected sets can be just these 1, 2, 3, 4, 5, 6, 7 possible infected sets. So this is the main point, key point where our we can utilize this side information to obtain some results where even when the prevalence rate is high, even with many infections in the system, we can get some nice results and huge improvements.
Great, yeah, that's really nice. And just a quick follow-up. So how high is high? As in, how high can it go before?
Let me just. Yeah, for instance, in those exponential split cluster formation tree structures, we know that expected number of infections can be order of n over log n in these systems. So one of these possible cluster formations is chosen uniformly randomly. And out of these order of n over log n expected infections, with just order of log n required test, we can design this zero error choice of sampling cluster formation. So these are the numbers. And like normally with this order of n over log n expected infections, for comparison, this adaptive group testing capacity is just like, again, like order of n log n, n over log n, with this assumption of exact known number of infections even.
Okay, thanks.
Thank you.
Okay, so Pantelis, you have your hand raised.
Hi, thank you very much for the great talk. Really enjoyed it.
Hello, thank you.
I was wondering if you can comment on the role of test sensitivity and specificity in all this, like if you can expand maybe the theory or the numerical results.
Okay, so that's a great question, because like in practical applications, of course, that test sensitivity is a great issue. I mean, like in practice, we know that all these theoretical works immediately assume that we have, when we mix those samples, it's like a logical binary OR channel. Like this is just the, having perfect binary OR of these positives and negatives. However, test sensitivity is is an important aspect of these practical applications, and these works all can be expanded to these considerations of test sensitivity. In our models, initial models, frameworks, we do not consider test sensitivity, but that's a great question.
Thank you.
Thank you.
Very much.
Thanks. Sophia.
Hi, thank you, welcome for a really nice talk. It was very interesting. I had one question or a clarification. I don't know if you could go back to the slide where you had this inequality with 1/2 that determined when one of the algorithms was superior to the other one.
I think this one, right?
Yes, I think so. Would you mind telling exactly in terms of which of the metrics would be the superiority? Because I can imagine, is it in terms of reaching the control of the epidemics faster, or is it in terms of the susceptible people not infected at the end?
I just missed talking about these things. So our performance metric is that the number of expected susceptible individuals at this steady state. However, normally, this is the performance metric of the that we consider. However, in this expression here, this is just at time t, which algorithm identifies more infections. This thing just says that.
Thank you. One quick follow-up. Can you imagine situations in which, if you have these two different metrics, controlling the epidemic faster and number of saved cases, if you wish, could be conflicting, and there would be a trade-off in between policies?
Yeah, actually, in our follow-up work that we also have here, this first conference paper that would be in the archive in a very short time, that we consider another performance metric, as you said, controlling the epidemic faster. So these two performance metric might be conflicting, or for some cases might not be, like they might be at the same time better. But here we saw that by using this dynamic saffron algorithm, that's a novel algorithm at that point, we see for some parameter sets, there is this kind of a conflict where one algorithm controls it faster, but with lower number of expected susceptibles at the end, as opposed to the other one. Yeah, so there might be some specific algorithms and specific parameter sets that might be the case, this conflict.
Thank you.
But again, it's a nice question, and it's like a very nice way of expanding these works.
Thanks.
Thank you.
Mansoor, would you like to ask your question?
Hello.
Hi. Hello.
Thanks very much for the talk. So as I was thinking through your version of group testing versus, as you call, the classical version, is it fair to say essentially you're just adding some prior information to the original signal? And in particular, are you not just adding some knowledge of the support of the solution of the signal? Because it's quite surprising, I think, as David said, is that you don't include sparsity in your log 2 of n, for example. So I guess it's not surprising that you can get a lower number because you just add more prior information.
Yeah. Basically, this is a valid interpretation. I mean, what we do in our first work is that we further assume this known statistics of these connections of people. Yeah. So as I said, this eliminates many possible infected sets. So as you said, this might be just thought of utilizing some given side information. And of course, like, it makes sense that this utilizing given side information would result in better, improvements, of course, in terms of number of required tests. It's expected. But the thing is, this is the way of, we try to model the practical scenarios, because like this side information is not something like we assume, and it's not realistic to assume. Like, we do not assume this given side information to just help us. We do not do that. But we know that, for instance, like data of these connections, like these probability estimations, can be done in practice. We know that we have mobile location data, big data in those tech companies, and like this can give us some estimations of these probabilities between interactions of people. And that's what we try to do by using this possibly available side information. Can we utilize this well enough to have some improvements? As you said, it's expected to have some improvements because it's side information, of course. If we did not have it, might be like our work might be like wouldn't make sense, because like it would mean that we couldn't really utilize the side information. But yeah, here we should try to show that.
And I have a follow-up question, if you don't mind. You skipped over the bit which I was most interested in, which is if you can go possibly to slide 16.
Yeah.
Which is the construction of this F-separable test matrix you talked about. I think that's one of the most interesting parts of this, where you can squeeze a lot of efficiency out of the number of tests to the number of samples. Can you just spend a little bit of time talking about that, please? Thank you.
Yes. Yeah. So here I can just go over this toy example again, and here just very briefly talk about our main ideas about this construction of F-separable test matrix. So here we have, for instance, these possible cluster formations, and we select a specific sampling cluster formation and select the individuals according to that specific sampling cluster formations. And in this toy example, if we select this F3 to be the sampling cluster formation, and if we select the individuals 1, 3, 4, 6, and 8, we know that out of these 1, 3, 4, 6, and 8, these individuals, these possible infected sets occur when some other possible cluster formations, if they are the true cluster formations. If F2 or F1 is realized in the system, for instance, yeah, in this example, let's say that F2 is the true cluster formation, and the patient 0 is the individual 6. It means that all these, 6, 7, 8, 9, 10, all these individuals becomes infected, right? However, we've selected sampling cluster formation F3 to be our sampling class function. We picked the individuals according to that. So we selected 6 and also 8. So basically, it is possible that 6 and 8 both can be infected, right? If F2 or F1 is realized and that patient 0 is in these specific clusters. So in order to model this and have a generalized result for this required number of tests, we first model these tree-like structure of cluster formations, and at each node, we just represent each node with some binary vectors. So these binary vectors must satisfy some specific criteria to represent a valid F-separable test matrix. So we need to have at each merging, so after assigning these binary test vectors, at each merging, these binary matrices, when going one level upper in the possible cluster formations, these need to be binary ORed. So for instance, here we see that we have 1, 0, 0 and 0, 0, 1 at the right bottom. And whenever they merge, they must have 1, 0, 1 because they must be the binary OR of each other. And whenever there is no splitting or merging, we cannot change the test matrices, test vectors. So basically the problem is finding the shortest such vector length that we can assign such possible binary vectors to all of these nodes, where these mergings, whenever the merging happens, it must be the binary OR of these specific child nodes. And also all of these test results must be unique, because at the end of the day, depending on who is infected, for instance, if 6 and 8 are infected and 1, 3, 4 are not infected, so if the 6 and 8, this specific cluster is infected, it means that if we design a test matrix like this, we basically take the binary OR of these columns 6 and 8, and the test results would be 1, 0, 1 in that case. So if we see that 1, 0, 1, we need to map it back to the 6 and 8 people. So in order to guarantee that, all of these possible test results, binary test results must be unique. All of these possible, some T length vectors, binary vectors must be unique. So the problem here at that point just comes to the finding minimum length of such binary vectors that we can guarantee finding these assignments to the nodes. Yeah. So
yeah, thank you. That was clear. I hadn't appreciated that your construction of the test matrix was based specifically on the structure or the clusters. So thank you.
Yeah. It was. Thank you. It was based on the structure of the clusters, as you said.
Great, thank you. So unfortunately, we're out of time, but thanks again very much, Fatih, for a really good talk. And yeah, if there are any questions, follow-ups, then I'm sure people can email you and continue the conversation. So thanks again.
Thank you for your invitation. It was a great environment. Thank you.
Thanks everyone.
Thank you.